Next, let us explore a first-in, first-out data structure called queues. Every time you order food at a restaurant, your order joins a line. Imagine a busy restaurant counter during lunch hour. Here, tasks arrive and sequentially take their place, establishing the order of processing. This continuous stream of incoming tasks creates a clear sequence, ensuring that each new item finds its designated position without disrupting the established order. The kitchen processes orders in the exact sequence they arrived. First order in, first order out. This is a queue. And it is how real systems manage fairness, prevent chaos, and ensure nothing gets lost. The kitchen does not pick randomly or jump to the easiest dish. They follow the line. This illustrates how the first item to enter the queue is the first one to be processed and removed, maintaining strict order. The principle of first in, first out ensures that every task is handled systematically. This prevents arbitrary prioritization and guarantees that all pending work will eventually be addressed in its due turn. This consistent processing flow is fundamental to managing resources and ensuring predictable system behavior. From simple task lists to complex operational pipelines, queues operate with two primary access points: the rear for adding new items, known as Enqueue, and the front for removing items, known as deques. These actions can occur independently or in synchronized pairs, ensuring a continuous flow of tasks through the system. A critical advantage of the queue model is its guarantee of fairness. Each item is processed in its exact order of arrival, preventing any skipping or reordering that could lead to unfair service or system chaos. This guarantees fairness with no skipping and no chaos, ensuring predictable and equitable task processing. This simple rule powers everything from printer jobs to customer service systems. Queues provide a fundamental building block for managing concurrency and resource allocation in diverse technological environments. By the end of this video, you will understand how queues work, why they are essential in real systems, and how to implement them to solve ordering, scheduling, and task processing problems in your own code. Let us start by seeing the principle in action. A queue is like a line at a ticket counter. You join at the back, and people leave from the front. Whatever enters first leaves first. No cutting, no jumping, pure order. This visual representation allows us to understand this fundamental principle of sequential processing. Let's break down the mechanics. A queue has two key operations: Enqueue, which means adding an element to the rear, and deques, which means removing an element from the front. Think of it as two separate doors, one for entering, one for leaving. To keep track of where things are, we use two pointers: front, which points to the element that will leave next, and rear, which points to where the next element will be added. These pointers are crucial for managing the queue's dynamic state. Let's see this in action with our restaurant orders. Order 1 arrives and joins the queue at the rear, illustrating the Enqueue operation. Order 2 arrives and joins behind it, further demonstrating how new elements are always added to the rear of the queue. With elements now inside the queue, we can clearly see how the front pointer indicates the next item to be processed and leave, while the rear pointer marks the precise spot for any new arrivals. This dynamic labeling reinforces the queue's essential behavior. Now the kitchen is ready to process. They deques order 1 from the front. As order 1 leaves, the front pointer moves forward, and order 2 is now at the front, ready to be processed next. With order 1 successfully processed and removed, the queue now holds only order 2. The front pointer has updated to reflect its new position at the head of the line, clearly showing the next element ready for processing. This demonstrates the queue's dynamic state and current size. This two-ended access pattern is precisely what makes a queue function as a queue. It enforces strict discipline, ensures first in, first out order, and prevents accidental data corruption by managing entry and exit points separately, ensuring a smooth flow of operations. Now let's transition from the metaphor to the code. In Java, we can implement a queue using the queue interface from the Java Collections framework. We'll use a linked list as the underlying data structure, which gives us flexibility and dynamic sizing. We start by declaring our queue. Queue, angle bracket, order, angle bracket, queue, equals new linked list, with empty parentheses. Let's create a queue of order objects. This class structure explicitly defines the contents of each order object, ensuring that every item in our queue carries a unique identifier and its specific dish name, which is crucial for managing diverse requests. Now let's enqueue some orders. We create an order object, order1, burger, and call queue.add, passing in the order. The order enters the rear of the queue, just like in our restaurant. We add a second order, order2, salad, the same way. Now the queue contains two orders. To process an order, we dequeue from the front. We call queue.poll, which removes and returns the front element. If we print the result, we get order 1, burger. The queue now contains only order 2. Before dequeuing, we should always check if the queue is empty using queue.isEmpty. If it returns false, it's safe to dequeue. If true, the queue is empty and polling would return null. We can also peek at the front element without removing it using queue.peek. This is useful when you want to inspect what's next without disrupting the order. Notice how the code operations add, poll, isEmpty, peek map directly to the physical queue behavior we saw earlier. The queue in Java works exactly like the restaurant queue. First in, first out, with strict two-ended access. Queues aren't just a classroom concept. They power the real world. Your computer prints documents in the order you send them, not randomly. Queues prevent document chaos and ensure fair access to shared printers. Call centers use queues to assign support agents fairly. First caller gets served first, preventing frustration and ensuring no one waits indefinitely. Your operating system's CPU processes tasks in queues. Without queues, high-priority tasks would starve, and the system would crash. And in distributed systems, message brokers like Kafka and RabbitMQ handle billions of messages daily. Queues decouple services, ensure reliability, and handle traffic spikes gracefully. But here's the thing. The restaurant queue we explored is just the beginning. Real systems face challenges. What if the queue gets too large and runs out of memory? What if items have different priorities, like an emergency order that needs to jump ahead? What if multiple kitchen workers are dequeuing simultaneously? How do we prevent collisions? These are the advanced topics: priority queues, circular buffers, thread-safe queues, and deques, double-ended queues. If you want to master these concepts and become the engineer who builds reliable, scalable systems, this is just the first step. Dive deeper, keep learning, and you'll be ready to solve the hardest problems in computer science.